In this presentation, I will discuss the modal model of a structure and how we can use it to describe the vibrations of the structure. We will discuss some key concepts: vibration mode, system pole, mode shape, forced motion, and the modal model. In a previous presentation, we concluded that the vibration system has a set of vibration modes, and those are defined by a parameter Sm, which is the system pole of the system corresponding to mode M, and a mode shape vector corresponding to the mode M. So each system have a set of pairs of poles and mode shape vectors. And together, this set of vibration modes is a system property that we can use as a model to describe the system's vibration. And this is what we are going to use in this presentation. So let us return then to our inhomogeneous equation of motion for the system. And for sake of simplicity, we consider the case without losses. So the damping matrix D is equal to 0. So this is now the governing equation, the equation of motion. And if we use the Laplace transform on this, we get this algebraic linear system of equations. And we can show then that this is a linear system of equations with a positive definite system matrix. And then we can use some useful theorems from linear algebra. First of all, the set of eigenvectors is a complete base for this system. So if we can use the set of eigenvectors, all possible solutions, vibrations in this case, can be expressed as a linear combination of the eigenvectors. This is what the term complete base means. So this means that the vibration x, displacement for instance, can be expressed as a linear combination of the eigenvectors phi1 to phi m. Phi1 here is mode shape 1, and the coefficient psi1 is denoted the modal amplitude of mode 1. Some more linear algebra. One can also show that the eigenvectors are mutually orthogonal. And this means that we can transform the physical x-coordinates to a modal space using a transformation matrix where the eigenvectors are the base. And that will give us a diagonal system, an uncoupled system. So if we introduce now a mode shape matrix as a matrix with the eigenvectors as columns, so the mode shape matrix phi here is a matrix with the eigenvectors as columns. So first column is eigenvector 1, and so on up to the final last eigenvector phi m. So if we return now to our inhomogeneous system of equations, like this, we can transform. Well, if we want now to make use of this mode shape matrix and its orthogonality properties, we can multiply from the left. And we get this system of equations then. And the right-hand side of this equation is denoted the modal force, that is the physical force Fs projected on the modal space by multiplication with this mode-shaped matrix. Okay, so then we can transform from physical to modal coordinates. That is, we can shift, we can change the physical space x to a modal space with modal coordinates. And that we do by introducing a new set of modal coordinates, xi, by this transformation. So the relationship between the physical coordinates x and the modal coordinates xi is this mode-shaped matrix. So we simply replace x here with this phi xi. So we obtain this relationship. And then we can use the matrix orthogonality properties. See, if we perform this matrix multiplication, we can see that due to the orthogonality properties, since this factor multiplying s square here, we can call mu, and this factor multiplying xi, we can call kappa. And these are diagonal matrices because of the orthogonality properties. The mu matrix is denoted the modal mass of the system, and the kappa matrix is denoted the modal stiffness matrix of the system. And the ratio of these two, the ratio of the nth diagonal element of the stiffness matrix and the nth diagonal element of the modal mass matrix can be shown to be equal to the eigenvalue n. So, if we continue now with the inhomogeneous equation, if we now multiply from left with the inverse of the modal mass matrix in order to solve this equation, we find that while mu inverse times mu will become the identity matrix, and here we have this matrix, the product of the inverse modal mass and the modal stiffness, and the right hand side like this. And this matrix now on this side is a diagonal matrix, which is easily inverted, and furthermore we can replace this mu inverse time kappa with the eigenvalue matrix given by this diagonal matrix. So it's on the diagonal we have the eigenvalues. So the system equations now reads like this, and this can be shown to be a uncoupled system of equations. So it's actually capital M, independent linear equations with solution equal to, if we look at component n, we can write the solution xi n as the modal force Qn over the modal mass times s square plus the eigenvalue. And what is this? How can we interpret this? Well, if we look at the modal sort of frequency response function of component n, then we can define this as xi n over Qn. So this is a motion, a vibration motion, and this is a force. So this is sort of a frequency response function of type displacement over force. And if we replace the s here with I omega, we get minus omega squared, where omega is the angular frequency. And this is, well, Sn here is the eigenvalue is of course the modal stiffness over the modal mass. So this is, if we compare this with an ordinary mechanical mass spring system with stiffness K and mass M, we see that this is nothing but equivalent to a mass, well, single degree of freedom mass spring system with eigen-angular frequency given by K over M. So if we plot this versus a frequency parameter, we find, well, if we plot the absolute value of the frequency response function versus a a frequency parameter given by the angular frequency squared over the eigenvalue, we find that we start from low values, and then as we approach 1, that is angular frequency equal to the square root of the pole, system pole, then we approach infinity. And then as we increase above this the eigenangular frequency, we approach 0 from infinity again. Now, if the system contains losses, then of course this infinity point here, the singular point, will be finite. We will get a finite result here. So here we have the resonance angular frequency. So, to conclude, in the modal space, where the eigenvectors are base vectors, we can interpret vibrating systems as a sum of uncoupled single degree of freedom systems, like this. Secondly, any motion of the system is a combination of modal contributions. So any arbitrary motion we can treat as a sum of contributions from these modes, uncoupled modes.